That we have 18 talks, and I believe you're number 6, so we're not quite halfway there yet. But we will achieve halfway this particular week. We have Madeline talking tomorrow at 4:30 in this room about HIV inhibitors. And then we also have on Friday Wyatt speaking at 3:10 in this room on MOFs. Four, sorry. It's 4, instead of 4. Also want to remind anybody that has yet to sign up for the chemistry department picnic, which will be the 23rd of May at 4:30 after Andrew's talk. Andrew's somewhere in here. Oh, there's Andrew, right after Andrew's talk right there. He'll be plugging that. Make sure you sign up so that Daniel knows to get the right amount of food. And that's outside the stockroom. So without further ado, my pleasure to introduce Lara. Had her in class, and it's always so nice to have her. In particular, it's always nice to have those analytical chemistry students who then absolutely freak out when first day in lab, it's like horseshoes, hand grenades, nuclear. As long as it's close solution making, it'll be just fine. And the students start to twitch just a little bit, right? And it's like, well, what volume? Where's the volumetric flask, Dave? Don't worry about it. As long as it's close, we're good. And so she hung in there and suffered through that really nicely, and it was great from that particular standpoint. But anyhow, she is going to be pursuing from Madison, Wisconsin. Is going to be pursuing a master's at the University of Minnesota, a master's in environmental chemistry. So without further ado, Lara.
Hi everyone, as Dr. Dave said, my name is Lara Frankson, and today I'm going to be talking about shrinking technology using polymers to print smaller circuits. So I'm assuming everyone in the room either has a cell phone or is pretty familiar with cell phones. And the cell phones that we have today are much different from the cell phones that first came out. So when cell phones first came out, they're these giant, huge brick phones. They pretty much, you could call someone, you could receive a call. There weren't that many other features on these cell phones. However, throughout time, our cell phones have gotten smaller and we've added more features. So, for example, on this Nokia phone, you might have a game or two, you might be able to text someone, make some calls, but besides that, there aren't a ton of other features. And despite adding these new features, we have continued to make these cell phones smaller. But now we're in this trend of this evolution of our cell phones, where cell phones are actually getting bigger. We're still adding more features. We now have apps, we have Wi-Fi, internet, all of these different features now on these phones, but our cell phones are getting larger. And one reason behind this is because of circuits. Now, circuits are like the backbone of our cell phones and much of our electronics. They are what connects all of our different components together. And so they're really, really important for our cell phones in order for them to be able to work. And without them, our cell phones would not be able to function. And right now we're stuck at this 10 nanometer barrier for printing our circuits. We can't print our circuits smaller than 10 nanometers in detail. And we're trying to get past this barrier so we can continue connecting more and more functions of our cell phone together in smaller areas. So I mentioned 10 nanometers, but how small really is that? For reference, a strand of human hair is 80,000 to 100,000 nanometers wide. So much, much larger than this 10 nanometers. Something a little closer in scale is a strand of human DNA, which is about 2.5 nanometers wide. So we're talking about something that's a lot closer in size to this 10 nanometers. And so with that, it's pretty impressive that we're already at this size in printing, but we still want to continue making it smaller so that we can continue making smaller and thinner devices with smaller and thinner circuits. So the way that we make these circuits is through nanolithography. And lithography is the transfer of a pattern onto another surface. And the nano part is just referencing the size scale, so at the nanoscale or very, very small scale. And with that, we have two examples of patterns. So these are from polymers, and I'll explain what polymers are in a little bit, but right now what's important is that we have two different parts. We have this lighter part, and we have our darker part. And with that, we apply this UV treatment. Now, if you're unfamiliar with what UV is, it's a part of the light spectrum, and you might be familiar with it through sunscreens. A lot of sunscreens protect against UV rays. And with that, we apply our UV treatment that preferentially gets rid of one part of this pattern, so one of the polymers, and in this instance it's the darker polymer, and we're left with these white voids. So with that, we now have a pattern we can use. Instead of just being a flat surface, we have these grooves, and we can pattern our circuits using this. And these are just two of the different types of patterns you can have for circuitry. There are a lot of other patterns that are available to use. And so I mentioned about a polymer, or I mentioned a polymer before, but what exactly is a polymer? So we have this nice little graphic of these little molecule guys, and representing just basically what a polymer is. So each of these little guys represents an individual unit, and then they're holding hands, which signifies the linking together or the bonding. So with that, polymers are chains of a bunch of these units, usually 1,000 to millions of units long, so much, much longer than this short little graphic. And while this polymers may sound technical, they're actually in our everyday life. So they're in things like our spandex or our clothing, they're in things like our plastics or milk jugs, as well as in the rubber in our tires. So they actually are in a lot of our everyday life, and these are only a couple examples. And we're just trying to use these polymers in another aspect of our life. So with that, there are a couple different types of polymers that I'm going to be talking about throughout this talk. We have our regular polymer that I talked about before. It's just this bunch of these repeating units. They're all the same. But we also have a copolymer. So this indicates that they're not all uniform. So there's, in the sense that there are two different types of these polymers. So we have, instead of all just these gray little individual units, we have some gray units and we have some orange units. So just distinguishing the fact that they're not all the same unit. And within a copolymer, we have two different types of those. So we have a random copolymer, which true to its name is an unorganized formation of this polymer. And so once again, we have two different parts. We have our orange part and we have our green part of the polymer, and it's in a random order. On the other hand, there's a block copolymer. And so this, once again, we have our orange part and our green part, but this time it's a very ordered, organized way. So we have 4 green, 4 orange, 4 green, 4 orange, and that continues on. So you can think about this like its name, it's blocks. There are blocks of orange, blocks of green, and they repeat. So the way that we use these polymers for this nanolithography and for printing the circuits is by starting with a surface. And so with that surface, we add on top our block copolymer, so our orange, green, alternating. And then we add our UV treatment. It preferentially gets rid of one of the polymers, so the orange polymer in this instance, and then we're left with this pattern. So this is actually a side-on view, whereas a couple slides ago when we talked about nanolithography, that was a top-down view. So it looks really simple and like, why would we even want to do this? But this is just the simplified side-on view versus that top-down view, which is a much more complex pattern. And where my research comes in is the fact that this does not occur. Instead of getting this perpendicular orientation of the block copolymer to the surface, we get this parallel orientation. And we can't use that because if we apply the UV rays, it's only going to degrade that top layer, that top orange layer preferentially, and it's going to leave the rest of it. So we don't get a pattern that we can use to pattern our circuits. So why does this happen? The reason behind why this happens is hydrophobicity. So to explain this, we have a glass of oil and water. The water is at the bottom in the blue, and the oil is in the yellow, much towards the top. And it's bubbling up because there's a seltzer tablet at the bottom. It's not just magically doing that. And so you can see here that they're not mixing together. And the reason behind this is that water is highly hydrophilic, and so philic relating to liking and similar to water, whereas oil is highly hydrophobic. And so phobia meaning fear of, and hydro meaning water. So they are complete opposites, and two hydrophilic things want to be by each other, and two hydrophobic things want to be by each other. So two like things want to be by each other, whereas when you have something highly hydrophobic and something highly hydrophilic, they do not want to mix, they do not want to be by each other, which is why these little beads of water form, and the water goes back down to this to the rest of the water to avoid mixing. And so to apply this to why our block copolymer does this different orientation, we go back to the individual units of the block copolymer. So if we have a green part that's hydrophobic, whereas the orange part is more hydrophilic, then if we have a surface that is more hydrophobic, the green part is going to orient itself closest to this hydrophobic surface, and it's going to cause this parallel orientation. On the other hand, if we have a hydrophilic surface, the opposite is going to happen. The orange part, or the hydrophilic part of the block copolymer, is going to orient itself closest to the hydrophilic surface. And so in order to avoid this parallel orientation, we need a non-preferential surface. We we need a surface that is neither hydrophobic nor hydrophilic in order for there not to be any preferentiality in the way that the black copolymer orients itself, and thus we achieve a perpendicular orientation. And the way that we propose doing this is through a similar method to before, where we start with our surface, and then instead of immediately adding on our black copolymer, we add on this blue strip. Now this blue strip represents our random copolymer, which if you'll recall is this unordered, unorganized way of having the formation of this polymer. From there, we add on our black copolymer and hope for a perpendicular orientation of the black copolymer relative to the surface. And this is because we are wanting to make a random copolymer that is non-preferential, so neither hydrophilic nor hydrophobic. From there, we apply our UV treatment, and we get our pattern. So this is the basic steps that we are hoping to do, and we're hoping that will work in order to achieve this perpendicular orientation. So the polymer, the random copolymer that we chose to work with was this MMA HEMA GMA random copolymer. So it's not in the order that it's shown up here. This is just to show the three components, and it will be a longer chain that is in a random order. So our GMA on the end, that actually is not playing to our hydrophobicity or hydrophilicity. That is there as a crosslinker. And what a crosslinker does is, so when we are making these random copolymer strands, there's more than one strand in the solution. And we want them to be connected to each other and to make a coherent solid and have a coherent surface. And so what this does, this GMA, it connects those individual strands. So our MMA and our HEMA are our main components that affect our hydrophobicity and hydrophilicity. And the OH at the bottom of our HEMA makes it more hydrophilic than the MMA, which does not have this OH, and so that is more hydrophobic. And with that, we decided to make 4 different compositions of this polymer in order to test and see when we have a hydrophobic or a hydrophilic or a non-preferential surface. So with that, we started with a 71% MMA, a 15% HEMA, and then a 14% GMA composition. Because our GMA is only being used as a crosslinker, we will keep that composition of the GMA consistent throughout these 4 compositions. Then we have 61% MMA, 25% HEMA, 51% MMA, 35% HEMA, and then lastly 41% MMA and 45% HEMA. So in order to go through and see if this random copolymer is hydrophilic or hydrophobic, there are a lot of steps we need to go through. First, we need to polymerize, or we need to make this polymer. So we're going to add in our 3 components of the random copolymer, our MMA, our HEMA, and our GMA, something to start the reaction, our AIBM, and something to put it all in the solution, anisole, that's our solvent. And the way that we did our polymerization was free radical polymerization. So I'm going to go through and explain what exactly this is, and it's not going to be specifically for this random copolymer, it's going to be just a simpler example of this. So we start with a molecule, and then we add in the Z star, which is our initiator. And so that star represents a free radical, and a free radical is an unpaired electron, and electrons like to be in pairs. And so right now it's pretty unhappy. And so what happens is it finds this first molecule on your left side, and it takes an electron from that double bond, forms a bond with that carbon, and then we're left with an unpaired electron, or this star on the end, which is also unhappy and doesn't want to be like that. So our Z star in this instance, or our initiator, is AIBN. So this molecule right here, which breaks up into those 2 molecules, and you can see from that middle carbon on the right side that there's a star there indicating a free radical. So that's where our Z star is in this instance. And what's really nice about AIBM is that we don't need to subject our experiment to weird conditions. It just needs to be exposed to light in order for that reaction to happen. So it's really easy to work with in that sense. So once we have formed this molecule on the right, it finds another one of these molecules in the solution and reacts again, doing the same thing, and that continues on and on to form a long chain. Now the way that this reaction ends is through 2 of these chains finding each other and reacting with their 2 unpaired electrons, pairing those electrons, and then forming this long polymer chain. And this happens because there's not just one polymer chain being made at a time. There are a bunch of different AIBN molecules being broken up and a bunch of different free radicals starting different reactions to make these polymer chains. And once again, these polymer chains are thousands to millions of units long. So they're not just little short units. They're very, very long units. And so what we did to make this molecule is we first tried by just putting together our MMA, our HEMA, our GMA, and the specific compositions that we wanted, adding our initiator, our AIBN, to start the reaction, but we didn't get that out. So instead we got this really gross gel that was impossible to work with, and we could not get the polymer out, no matter how hard we tried. So the reason that this occurs is because we have this OH on our HEMA, which ring opens this GMA, and then forms a bond there. And that's not where we want this reaction to happen. We want our polymer to be formed up towards that top along those carbons. And so we kind of go back to the drawing board, figure out how are we going to make this polymer without having this reaction occur. So the next thing we tried was using THP protected HEMA. So instead of just having this OH at the bottom of the HEMA, we changed that to this ring group. And so now this ring group cannot react with that GMA. With that, we added our AIBN, our initiator, to start the reaction, and then we got out our THP HEMA with our MMA and GMA random copolymer. So we haven't quite gotten to the exact random copolymer we want. We want that to be just regular HEMA and not THP protected HEMA. But in a couple of steps, you'll see how we get rid of unprotect this group and get back our regular HEMA. So right now, we've made this random copolymer. It's not quite what we want yet, but we'll get there. So we made this molecule, or this polymer, and then right now it's in solution, so we need to precipitate it out or get it into solid form. And with that, we drop the polymer dropwise into a solution of hexanes and diethyl ether, and then it precipitates out. From there, we then redissolve it, and then we spin coat it. So this is how we get our random copolymer on top of our surface. And our surface in this instance is a silicon dioxide wafer. And so we put the silicon dioxide wafer on top of a spin coater machine. So there's a little part we put in a spin coater machine. It spins around at about 4,000 RPM. And we drop a couple drops of this polymer on top, and it creates a nice uniform surface of our random copolymer on top of this wafer. From there, we thermally anneal it. So what this step does, and what this is a vacuum chamber that heats up. And because of the fact that we spin coated this polymer on top of this surface, it's kind of all disorganized, and heating this up in a vacuum chamber allows it to kind of settle down into more equilibrium position and a little bit more ordered. And we did this at about 220 degrees Celsius for 3 hours. And this is where we actually did this deprotection of the THP group. So through this thermal annealing, we deprotected this THP group into regular HEMA. And we know this because when we first tried it at 160 degrees Celsius, it did not deprotect, but then when we did it at higher temperatures at 220 degrees Celsius, it did end up deprotecting. So now we have made the random copolymer we want. And the last step is to incubate it in water. So we have this wafer with a random copolymer on it, and we incubate it in water for a couple hours. Well, this may seem trivial. It's actually really important because it allows us to have a more uniform surface. So if you recall, the HEMA part of this random copolymer is more hydrophilic, and so they'll orient the more hydrophilic parts closer to the surface, and it'll allow for just more uniformity in the orientation of this block copolymer. Sorry, in the random copolymer. So after we've done all of that, we need to characterize it. We need to see how hydrophilic, how hydrophobic it is, what have we made, make sure we have all of that in row. So the first thing we do is gel permeation chromatography. So that tells us about the molar mass of our random copolymer, so how big is it, as well as the dispersion. How uniform is this block copolymer? Are all of the chains 1,000 units long, or are they all over the place? So we get some data that looks like that. And then we also did hydrogen nuclear magnetic resonance, or HNMR. And so this tells us about the composition of our random copolymer. So did we make what we wanted to make, as well as the purity of it. So were there any weird side reactions that happened that we didn't think would happen, and how prevalent were they? We get some data that looks like that. So what these first two is kind of just confirming that we made what we thought we wanted to make, and just seeing what exactly is there. Where we really tell how hydrophobic or hydrophilic this surface is through contact angle measurements, which tell us about the surface tension, which then tells us about how hydrophobic or hydrophilic the surface is. And this data is a little bit more fun, a little less traditional in the fact that it's not a graph that you get out. Instead, you get this nice picture and that's a water droplet on our surface. So with that, I'm going to go a little bit into contact angle and how we used it and how it's used, how it becomes quantitative, because right now we just have a picture and it looks nice, but we don't have any quantitative data. So what is surface tension? So if you look, you have two surfaces, and you can have a water droplet look like that, or you can have a water droplet look like that. So you can have a much more broad one or a much more curved one, and that'll depend on your surface. So if your surface is hydrophilic, so it likes water, the water droplet is going to be much more broad. Whereas if you have a hydrophobic surface, then that water droplet is going to be much more curved. And so this hydrophobic surface is going to have the water droplet with a higher surface tension than this more broad one. And with that, the way we make it quantitative is through Young's measurement for contact angle. So we have our surface, we have our green, which is the random copolymer on top, and then we have this water droplet. From there, we have this intersection, which is the relationship between our surface tension between the liquid and the gas, the surface tension between the solid and the liquid, as well as the surface tension between the solid and the gas. And from there, we have our angle, which is our contact angle. And so if we have a hydrophilic surface that has a water droplet that's more broad, we're going to have a smaller contact angle than if we have a hydrophobic surface, which has a much more curved water droplet with a higher surface tension and has much higher contact angle. So this is how we can tell whether or not a surface is hydrophilic or hydrophobic and to what extent it is. So with that, we're going to go to some of the data that I took throughout this for our contact angles. And so we have water contact angle. And so we are increasing in HEMA, or the more hydrophilic part of this random copolymer, as we go from left to right. And we are then decreasing in MMA also. And you can see that as you increase the amount of HEMA, you have a much more broad water droplet because it's more hydrophilic. And we can look at the molecule and see this too. So we have that OH at the bottom of the HEMA, which makes it more hydrophilic, and thus when we have a water droplet and it's on a surface with more HEMA, it's much more spread out. On the other hand, we have chloroform contact angle. Now chloroform is essentially the opposite of water. It is highly hydrophobic, and so we can see the opposite pattern here. As we increase in the amount of HEMA, our water droplets become much more curved, and there's a lot higher surface tension and higher contact angles. So we have this general trend, and now what we do with that is we have this graph. So this just shows on the x-axis is our water contact angle, so showing how hydrophilic our measurements are, and then on the y-axis we have our chloroform contact angle, which is how hydrophobic. And we are decreasing the amount of HEMA from top to bottom. And so we have a pretty decent trend, a pretty decent R-squared value from this. And what's important to note is that for a truly non-preferential surface, we would need our water contact angle to equal our chloroform contact angle. So 60 degrees water contact angle and 60 degrees chloroform contact angle, for example. So with this particular polymer, or this random copolymer, that would be about 63, 64 degrees. So you can see our purple 25% HEMA right there is pretty close to that. It's not exactly that, and part of the reason why it might not exactly lie on that trend line is because when we make these random copolymers, they're self-assembling. So instead of us manually putting together each of these units of the polymer, it's self-assembling. And so we only have so much control over how much is going to be in each individual strand for percentage-wise. So while we may put in 25% HEMA, we might actually get out 24% HEMA or 23% HEMA, and that can alter our surface energy, that can alter how hydrophilic or hydrophobic it is. And so with that, in order to be able to use this polymer, we really would need to be able to really control this formation and consistently be able to get out this exact point on that star where it is equal contact angles. And so right now we haven't done that. These are averages from multiple measurements in multiple different films, but there's potential with playing with that and seeing whether or not we could be able to get it consistently at that point. So with that, where do we go? So as I talked about before, we need to find a non-preferential random copolymer. So we can mess around with this polymer, see if we can get exactly to where our chloroform and water contact angles are equal. But we also want to look at other polymers and see maybe if we can get something where they're both at 30 degrees and something where they're both at 90 degrees and see the effect that that has on our pattern abilities. So next we would also need to synthesize and to characterize more polymers. So just test around and see, if there are polymers that are easier to work with, that are faster to work with, that are easier for different parts, or that would give us different results. So we need to go back, polymerize a bunch of different polymers and see where we can go from there. Next, we want to study how the surface behavior is altered by environmental effects. So we need these to be more robust. We don't want to have to be working in a 5-degree temperature range or have to be worried about if we change humidities or something weird happens in the lab especially. So we need to go, we want to spin coat a bunch of these polymers on and then expose them to different environmental conditions and see if that changes any of our patterning or any of the surface energies. And lastly, we want to understand the mechanism of the deprotection of the THP group and its effect on surface behavior. So before I just kind of said, cool, we thermally annealed it, we put it in this chamber, heated up, and it disappeared. But we aren't entirely positive about how exactly that occurs. We have a couple thoughts, but we would like to dive into what exactly is happening there so we can better understand it and better understand how that's affecting our surface and if it's changing its energy. With that, I'd like to thank a couple of people. Dr. Padma Gopalan and Wei Wei, who helped me at UVA Madison, were my mentors throughout this research, as well as Dr. Dave Paul, Dr. Graham Sazama, and Dr. Allison Fleshman for helping me with this presentation. Questions? Yes, why?
Never heard of surface angle stuff.
Yes.
Is it, from what I got from this, it is a fancy picture, a really close picture, and then I'm assuming some sort of software that tells you the angle?
Yeah, so I don't know what.
If you could just speak more about the instrumentation or anything.
So, yeah, so with that, so you get this picture, and then there's a software that you kind of outline where the bottom is, so you outline where like that is. And it's assuming a level surface. But then you click a couple points and then it'll pop out a number for you. Does that make sense? Mm-hmm. Okay. Yes?
On that, you said that, so since we're worried about like whether you actually got a 25%, how reproducible is like if you do a drop on a surface again and again and again, are you getting the same surface angle? Like what are the errors bars associated with that? You said you did multiple surfaces, but did you ever do the same surface over and over again?
Yeah, no, we did each surface a couple, 3 times. So we would, on each wafer that we spin coated, we would do 3 different spots. They were pretty similar. I can't tell you exact error bars. That data's in Madison. But yeah, it wasn't like they were hugely different.
And you think that's bigger than that you think that can account for the deviation from the line, that you actually have to have a not quite meeting the
Well, what I meant from that
25%
was that when the polymer is being created, so like when we put in 25% HEMA and we then do like NMR from that, we're getting out like 23 or 24% HEMA instead of that 25%, and so we would have to alter how much we're putting of each percentage in order to get that truly like what is actually 25% HEMA out.
But you're getting that from the NMR data.
Yes.
Thank you.
Mm-hmm. Yeah, Allison?
I have 2 questions.
Mm-hmm.
One of them is, what sort of temperature control do you have in this set up for the contact angle? Just curious.
Not much.
Okay.
It's in a room in a basement.
Go team.
There's not like a special temperature control or anything.
Yeah. Because I was just thinking about the viscous properties of this water.
Yeah.
Or whatever, drops and stuff that you have. And so how susceptible is the polymer to temperature fluctuations? Or like, does it show any physical properties that change on temperature? Like, any sort of studies that y'all done on those?
So there's more been studies on like studies on how different temperatures and different conditions alter the initial formation, like up to that thermally annealing step through that. But we haven't quite looked, or I haven't seen studies on like afterwards how much those alter the properties.
So my other question is kind of related to that. So help me understand the picture. So you got the solid surface thing, and then you got, assuming that you did the UV treatment, then you got the block polymer bits, or the bits of the green ones, not the orange ones.
Yeah.
is that a solid phase, or is that like more of an amorphous phase polymer, or crystalline phase
Oh,
polymer?
that is not a slide.
So like what sort of phase is the polymer post-treatment, best case scenario, this is the material that's now printed?
What do you mean, like?
Yeah, no, well, so you're doing measurements about hydrophobicity, so it's a liquid-ish, but then, I know polymers
Oh,
are-
sorry. Yeah. Well, like, so it's not, like, the polymer is, like, you're saying is
Is it like a gel, is it like a?
Oh, no, it's,
Plasticky, that's not plastic, that's wood. But that's not a polymer, but you know what I'm saying, like, it seems like you want a hard surface.
yeah, it's a
but-
hard surface.
But it can interact with the surface to give you that angle, so it's just an
It's
interesting.
more, yeah, no, it's like, it's a solid surface. It's more like, so, like, you would put a drop of water in here, and like that would have a contact angle, but
Mhm.
there's these interactions because there's, like, yeah, it's like it's a solid surface. It's not that it's like a gel or anything.
Okay.
Like, you can't really see it on the wafer because it's like 15 nanometers thick.
That's how big those drops are?
No, the random copolymer surface.
Okay, I was like,
No,
what?
these are, the drops are
Sorry. Anyway,
microliters, couple microliters.
Okay,
They're really small.
cool.
Yeah. Or point. Yeah.
This is a lithography question, so it's
Okay.
okay if
You
that's
can
not-
go for it.
if that's not what you were actually researching. But when you're putting this random copolymer on top of your substrate and then the block copolymer on there, and then you're developing your block copolymer with
Yeah.
the UV light. If you want to pattern something on that surface that you have labeled, do you know how one is getting rid of the random copolymer, or does that become a part of the device?
There is an extra step, I believe, in that this part gets rid of, but I didn't want to focus on that.
Okay.
Yeah, so there's another step that I'm fairly positive that is gone, and so you can just use that, but not like, I would look it up too. Because obviously, like, I didn't focus, like, this is just
Yeah.
connected, and, you know, there's much more just focused on the random copolymer.
Other questions? Okay, let's thank the speaker.